Our final topic of the semester is going to be relativity. Now, previously we've kind of wrapped up most of what we're talking about with light and optics, but the ideas of light and optics carried over once those topics were finished out. They were carried over into relativity, and so let's talk a little bit about the basics behind relative motion. Now, we talked about relative motion in chapter 4 of the textbook. So we introduced the idea. One of the ideas would be, for example, you have a moving sidewalk at an airport, and you have someone standing on the sidewalk, and we have someone walking on the sidewalk, and they're walking at 2 feet per second. The sidewalk is moving at 3 feet per second. And so the question is, for someone standing here watching this, they see this person moving at 3 feet per second, and they see this person moving at 5 feet per second. And so this is the idea of relative motion. Okay. Another example here would be like on the highway. You have a car here, and that car, we'll call it car A, is driving at 55 miles per hour. We have another car here, and this car is driving in the same direction. We'll call it car B at 65 miles per hour. And then we have another car over here heading in that direction at 65 miles per hour. That's car C. So if you're a driver in car A and you look out to the side and you see car B, then it looks like car B is going at 10 miles per hour past you. In other words, it's just as if it's going 10 miles per hour and it's passing you. Whereas if you look ahead at the other car, it looks like it's coming at you at 120 miles per hour. And so, again, you got to make allowances for that as you're driving down the road, that it's coming at you and getting to you a lot quicker than if it weren't moving. Now, if you're in car B and you look at car A, it looks like it's going backwards at 10 miles per hour. Okay, and if you look ahead at this other car ahead, it looks like it's coming at you at 130 miles an hour. Okay. If you're in car C and you look at car A, it looks like it's approaching you at 120 miles per hour, but car B looks like it's approaching you at 130 miles an hour. Okay, so now the question is, well, who's right? We have all of these different ways of looking at it, and who is correct? And the answer is they all are. From their vantage point, they are all correct. And again, in Physics 1, we introduced the idea of moving coordinate systems. So I could put a coordinate system on this car that's moving at 55 miles per hour. So this car's not moving at all. That car's going at 10 miles per hour. That car's going at 120 miles per hour that way. And we can solve the problem. So instead of 3 things moving with 3 different unknowns, we reduce the problem. So we make it a little bit simpler. This way of looking at relative motion, both the previous example and this way, was done by Galileo. So this is what we know as Galilean relativity. And this is perfectly acceptable. It makes perfect sense. And this is chapter 4. Well, this is where Albert Einstein comes in, because Albert Einstein is now thinking here, okay, so we've got a spacecraft here, and it's going through space. You've got an occupant in the spacecraft, and a laser fires from the back of the spacecraft to the front of the spacecraft, okay, and then goes out this way. And so we know the light is moving at the speed of light, okay. And so now the question is, if your spacecraft is now moving so the velocity of the spacecraft is 1/2 the speed of light, and you have to fire a laser out this way, well, how fast is that laser going? Okay, how fast does this person see the light moving and how fast it's going in? Now, clearly, if you're an outside observer out here and you're observing, whatever's happening, then this light is coming at you at the speed of light. Okay, so the spacecraft's not moving. It goes past this person at the speed of light, hits here at the speed of light. Everybody agrees it's moving the speed of light. Whereas in this case, obviously it's still light. Okay, and so now if you are thinking Galilean relativity, if you've got, if you got something moving this way and you add a velocity to it, then the velocity is going to be the sum of the two. So would this person measure the speed of light as 3/2 the speed of light? We can't do that because the speed of light is the speed of light. We know the speed of light is 1 over square root of mu naught epsilon naught. Those are constants, right? So this person is measuring electric and magnetic fields. Because they're measuring electric and magnetic fields, they must measure that speed of light. Okay, so now the question is, as the light's passing this person, what do they measure? Do they measure the speed as 1/2 the speed of light? Well, that doesn't make sense either, because that also that person's also measuring electric and magnetic fields. Okay. So this is where Albert Einstein comes in here, and Einstein says it doesn't matter. Everybody's going to measure the speed of light the same way. So if you've got a spacecraft and you've got an astronaut on the spacecraft is going at 0.75 the speed of light, and you have a beam of light passing it, then a stationary observer sees the beam of light going at the speed of light, but the observer in the spacecraft also measures it going the speed of light. Likewise, if you have a laser shooting off of the spacecraft at the speed of light, someone over here measures it coming at the speed of light, this person measures it leaving the speed of light, but they're still moving at that speed right there. So, but it's still, they measure the same speed. Everybody measures exactly the same speed. Now, this turns out to be a quandary. And so how does all this work? Okay, and this is where Albert Einstein comes in here. And Einstein looks at this and says, okay, so the Galilean relativity does not apply in this case to light. Because Einstein says everybody measures the speed of light at the exact same number. So everybody's measuring the speed of light the same. And so this is one of the basic principles in relativity. If you then make this what we call the speed of light postulate, then he says that would mean that we would be able to derive what's happening physically that allows this sort of thing to occur. And so that's what this chapter is about. But the key is everybody measures the exact same number for the speed of light, at least in a vacuum. In a vacuum, you always measure the speed. Obviously, we know if it's not moving in a vacuum, if it's moving through a medium of some sort, then it's going to go a little bit slower. But in a vacuum, it will always measure the same speed. Everybody who measures it the same speed. So now we're going to investigate, what does that mean?